My name's Jeff Burdik. I'm a Senior Vice President, hydrogeologist for Arcadis based in Philadelphia. I'm the Global Solutions Director for Site Evaluation and Remediation, and I'm also the North American lead for our PFAS program. PFAS stands for perfluoroalkyl substances, and this is a rather complex group of chemistry that has some pretty unique properties. It's invented in the 1940s and 1950s. Because of this unique chemistry. These are carbon and fluorine bonds, which are some of the strongest bonds in chemistry and make these compounds very slippery. So they're used in a lot of commercial apparel and products for stain resistance, water repellency, but the carbon-fluorine bond is also thermally resistant. It takes about 1,000 degrees C to break that bond. So it's used for flame retardancy or fire extinguishment. It's used in firefighting foams. And that's really a lot of our focus on where it's used and where it can be found as a point source. These compounds are definitely unique in that they're not volatile, they're not strippable, they're generally not biodegradable. The only factor they have that we can take advantage of a little bit is the fact that they'll tend to absorb to carbon and they'll be retarded in soil a little bit. But it's a pretty weak adsorption compared to things like benzene. So what this means for us in the environment is we can have plumes that can be very long and much longer than what we've seen with MTBE or BTEX or even dioxane. They're also unique in that they're an emerging contaminant and we don't have a lot of toxicity. We only have toxicity info on PFOA and PFOS, and these are the two C8 compounds that have been regulated. Stockholm Convention, the EU, now the US EPA with its health advisory level, and they're regulated at a very low number, 70 ppt for drinking water, and the toxicity thresholds keep dropping. It's dropped by an order of magnitude in the past 10 years. The challenge though is that there's hundreds or thousands of other compounds present in these products that can have anywhere from 2 carbons to 13 carbons, straight chain to branch chain, and we don't know about the toxicity of the other things that are present. So that makes it challenging for us if we're trying to prevent exposure or we're trying to clean something up. Given those properties that I just reviewed, we can't strip them, we can't chemically oxidize them. Really the only thing we can do is adsorb them or partition them or fractionate them or concentrate them or thermally treat them. Thermal incineration is very expensive, so there's movement to identify cheaper, better, more efficient ways to treat these. But in water, we're typically trying to protect drinking water or clean up drinking water. So the de facto technique is granular activated carbon. It's fast, quick design, it's fairly simple. We can deploy it and be in the field in a matter of months. The problem is it only absorbs some of these compounds. It'll absorb the C8 compounds, but other things may break through. But there's other things that are alternatives to carbon. There's anion exchange resins, which are more expensive, but have a lot more capacity for adsorption, and they can absorb a wide range of perfluorinated chemicals that could be in the water. We talk about it in terms of future proofing, meaning if we have someone drinking the water, we may want the ability to add a resin onto that treatment train in case these other compounds are regulated, or to be conservative just to prevent exposure to these other compounds. There's other techniques like reverse osmosis or ozofractionation, nanofiltration, which basically just separate and concentrate to differing degrees the perfluorinated compounds out of the water. There's a lot of research in terms of synthetic adsorbents, and there's also some other techniques being developed that look at destruction, whether that's through sonolysis, which is high frequency sound waves, or electrochemical, which is based on moving electrons, cathode and anode. These have shown promise at the bench, but really not at a large scale. In terms of soil, generally we're trying to avoid putting it into a landfill because these are very leachable and very mobile. We're trying to avoid thermal incineration when we can, but there are the potential abilities to stabilize it in place, lock it in place with concrete, carbon, clay, such that the leachability is removed and we don't have a source that could affect drinking water.